We're going to talk about vertical acceleration today, or vertical kinematics. Good news is that you don't get new equations. You use the same ones that you already have. So we're just going to apply them to the vertical now instead of to the horizontal. We're still not dealing with a mixture of those two components, right? We're still doing all vertical or all horizontal. So we're looking at objects that are in free fall, what we consider free fall. Right? They're falling downward. And what's the only thing that's pulling them downward? Gravity, right? So that's what we're looking for. Okay, so anything in free fall is still considered to have an acceleration. And that acceleration, that constant acceleration, is the acceleration due to gravity. Okay? So knowing what we know about gravity, try to answer this question. Do heavier objects fall faster than lighter objects? Yes. Okay? So if you drop a ball that's hollow and a steel ball at the same time, we think the steel ball will hit the ground first, right? Wrong. What? Nope. Nope. Okay. The answer is no. As long as these two things are shaped the same thing and air resistance would affect them the same way, they're going to fall at the same rate. Tricky, right? We're going to watch a video about it. Okay. So, anything we said is free falling is acceleration due to gravity. We're going to use our kinematic equations with G instead of A, but I'm not going to make you substitute that letter in and write a whole new set of equations. That seems silly. So as long as you know that the A stands for acceleration due to gravity on vertical problems, and we're always going to plug in negative 9.8. Right? So for vertical problems, all vertical problems, negative 9.8 is your acceleration. For horizontal problems, our acceleration changes. Right? But for vertical problems, it's always negative 9.8. Okay, since motion is vertical instead of horizontal, we're going to use Y for our positions, initial and final, instead of X. Okay, again, I'm not going to make you rewrite a full new set of equations, but when you're thinking vertical, you might want to use Y. Okay, suppose that a ball is dropped from a tower 70 meters high. How far will it have fallen after 1 second, 2 seconds, and 3 seconds? Okay, so I'll give you a second to get it written down, then we'll talk about how we draw our diagram and where we start for this one. Okay, so when we draw our diagram, here's our little cliff, right, or our tower, whatever. Okay, and I talked a little bit about placing the origin where our motion starts from. Okay, and that probably didn't make a whole lot of sense until we get to these vertical problems. Okay, so what I'm talking about is that the origin's not on the ground, right, because that's not where our motion is starting from. I like to choose my origin where our motion starts from. And the reason I like to do that is because we can tell how far we're ending up from where we started. Okay, so theoretically, if the ball fell all the way to the ground, right, if it made it all the way to the ground, which is not what this problem is asking right now, okay, but if it fell all the way to the ground, what would our final displacement be? Negative 70. Good. Why negative 70? Yeah, it's below where it started. Okay, and that's kind of a tough thing for people to kind of wrap their brains around a little bit, but that's why I put this up here. So it does make us flip numbers every once in a while, but I think it makes the most sense for the majority of the problems that we do is to put our origin where the motion starts from rather than on the ground, right? So I like to put it where it starts from. So again, that's not what our problem is asking us necessarily, but we just need to keep that in mind that if we wanted to find its final displacement here, it would be negative 70 meters, okay? But for right now, let's see what we're looking at here. We want to find how far it's fallen after 1 second, 2 seconds, and 3 seconds. So we'll have 3 different answers here, right? We can't do these all in one problem. We'll have 3 different answers. We want to find how far it's fallen. What variable are we solving for? Y, final, right? Final displacement. It's not falling all 70 meters after 1 second, right? Or we don't know that it has. So we're solving for Y, final. Okay, that's our question mark. What do we know about our initial displacement? It's 0, right? That's another perk of putting the origin where it started. If we'd put the origin at the ground, we would have had to say our initial displacement was 70 meters, right? Because it's 70 meters above the origin. So that's another perk of putting the origin where your motion starts from, is that you don't have to, you always have an initial position of 0. Okay, what do we know about its initial velocity? It's 0. Good. The term dropped tells us that the second it leaves our hand, it's now a freely falling object, and for that instant, it's not in motion yet, right? Until gravity really starts pulling it down. We know the acceleration is negative 9.8, right? So look, all three of these variables we picked out of the problem with no numbers, right? Those were not numbers that were in the problem. So those are things that you just have to know, right, and pick out by yourself. What equation should we use to solve for final displacement? If we've got time, initial velocity, the second one, right? So y equals y initial plus VOT plus 1/2 AT squared, right? Both of these terms are 0. Both those first two terms are 0, right? It's dropped, and our initial position is 0, so we can drop those first two terms. We end up with 1/2 negative 9.8 times 1 squared. Okay, so y equals negative 4.9 meters. Okay, so that means after 1 second, we've only fallen, like this far. Okay, negative 4.9, the fact that it comes out negative is telling us we're ending up below where we started. Okay, which makes sense, right? Because we're falling downward. Okay, so can you expect for 2 seconds that it's just going to be double that distance? No.
It doesn't make sense. Why does it always speed up as you go down?
Yeah, as it goes down, right? Every second that it's in the air, it's increasing by 9.8 meters per second. Right, so every second we're gaining 9.8 meters per second worth of speed. Right, that's what the acceleration is telling us. So as it falls, we're gaining speed, gaining speed, gaining speed. So that means we're falling a farther distance every second. Right. So let's go ahead and solve for it at 2 seconds. The only thing that changes in this equation is time, right?
Yep.
So y equals 1/2 negative 9.8 times 2 squared. Okay, that squared is what's going to get us there. So y equals negative 19.6 meters. Yeah? So now we're like maybe about here.
Yep.
19.6. Okay, so we see this little interval from here to 1 second is a little bit shorter than this interval, right? We've only fallen 4.9. Now we're falling to 19.6. So what we can expect this interval to be even bigger, right? So at 3 seconds, negative 44.1 meters. Yeah, do we agree?
Yep.
So we've fallen over halfway by that point. Okay, so we see with every second that interval that it's falling is getting bigger and bigger and bigger because it's gaining speed as it falls. Okay, does that make sense? So instead of dropping the ball, we're throwing it downward. Would you expect its displacement to be farther than 19.6 or less than 19.6? Farther, right? It's given an initial velocity to start, right? So that means it's starting with a velocity and it's gaining speed as it falls. So we would expect it to have fallen a greater distance than 19.6 meters. So that changes our equation just a little bit because our initial velocity is no longer 0. Our initial velocity is what?
3.
Positive 3 or negative 3? Negative 3 because it's going downward. Okay, I did that on purpose. I worded that like that way on purpose because I wanted you to see that. Okay, because if I said positive 3, that means we're throwing it upward and then it's going to reach its highest point and then it's going to fall. That's not the picture that we're trying to depict here. Okay, time is 2 seconds. Initial position is still 0. We're solving for final position. So So now we can't drop both of those initial terms in our second equation. We can only drop the position, the first position one. Okay, so y equals 0 plus negative 3 times time plus 1/2 negative 9.8 2 squared. Agreed? Good. Okay, and that's what we expected, farther than 19.6? Okay, good. Person throws the ball upward into the air with an initial velocity of 15. Calculate how high it goes and how long the ball is in the air until it reaches his hand again. Okay, so in my diagram here, he throws the ball upward, right? And then the red path is the right way back down. Okay, theoretically, should those paths be symmetrical? Yeah, right? They should go up and come down in the same amount of time, right? As long as it takes to go up, it should take the exact same amount of time to come down. Just like it's the same meters on the way up, same amount of meters on the way down. So when we throw things vertically, we should have symmetric paths, right? They should look the same on the way up and on the way down. Okay, so just something to think about there. We throw the ball upward with an initial velocity. So V sub O is 15, and it's positive 15 because it's going up. Okay? Calculate how high it goes. What variable does that mean we're solving for? X or Y, right? Either way. Y final. Okay? If the motion starts here, right, that's where our origin is, which makes our initial position what? 0. Okay, now here's the thing we have to think about. At its highest point, at its peak height, okay, I like to use the term peak height. Okay, that's as high as it will go. At its peak height, what is its velocity? 0. Okay, so that means we right now are just looking at the trip up, right? That's all we're looking at, how high it goes. Because we're talking about that's its final displacement. So we're looking at only the first half of the trip. So that means our final velocity is 0. Are we on the same page so far there? Right? Yeah, the third one, right? Because we don't have time yet. So we got to use the third one. So 0 squared equals 15 squared plus 2a times y minus y initial, which is 0.
How do we know its acceleration is -9.8 if he throws it up?
Still, gravity's pulling it downward.
Silly.
Yeah, that's tricky. Gravity's negative no matter what, right? Gravity is always going to pull down.
How do we know
we have to
zero?
use gravity.
A final velocity is 0 because at its peak height,
The third one.
we're doing the third one,
I
yes.
was looking at the second.
Oh, sorry. We're doing the third one. Yeah, because we don't have time. So we got to use the third one. Okay, so that's something else that we have to pay attention to. No matter the direction of the object, gravity is always negative. Okay, whether it's going up or going down. Gravity is always negative. Excuse me. Okay, so 0 equals, I think 15 squared is 225 maybe. Negative 19.6 times 4. I didn't do that in my head.
First, that looks like it's a Y, right?
Yes, it's a Y.
You're good.
Sorry.
I was just like,
Oh my gosh, sorry. Where did that come from? Okay. I'm like, I don't know what. Okay. Yeah, I got you.
it's
Okay.
been a long morning.
Yeah, I'm telling you, I need to go home. Okay. All right, so 225. We need to move 225 to the other side first. So negative 225 equals negative 19.6 y.
Okay.
Okay, subtract that 225 over first. Then we'll divide by negative 19.6.
It's 11.48.
That's a lot. Pretty good. That's a pretty good throw.
Oh, yeah. How do you think you get that?
I feel like you get more velocity on it if you go underhand, right? Rather than go.
But you want to get it straight upward too in the hand.
That's true. Okay, 11.48 meters. Do we all agree? Get that to come out in our calculator, okay? Okay, so now we're looking at how long the ball is in the air until it reaches his hand again. So that's all the way up and all the way back down, right? Yeah, so here's the thing. You can use what I call the shortcut method, okay, which does not involve the quadratic equation, okay? Some problems we do are going to involve the quadratic equation, which I can't wait to get to. This one, for right now, we're not doing the quadratic equation. So what I'll show you is the shortcut method, and you can use the shortcut method anytime we have symmetric motion. So if it starts and it lands at the same height, you can use the shortcut method, right? If it goes up and comes back down in the same amount of time, you can use the shortcut. And the shortcut is simple. All you're doing is solving for the time it takes to reach peak height, and then you multiply it by 2. That's it, right? But if we have unsymmetric or asymmetric, asymmetric path, right? So this would be an example of an asymmetric path. I'm up on a cliff, I throw something in the air, and then it lands below, right? That's not symmetric. So we can't use a shortcut because it's not going to take the same amount of time to reach peak height as it would to reach the ground, right? But in our example, it takes the same amount of time to go up as it does to come down. So we can use what I call the shortcut method. Okay? So to solve for time that it takes to reach peak height, we can use our easy equation. Because we know the initial velocity is 15. We know our final velocity at peak height is always what? What's our final velocity here? 0. Okay? So that means we can use our shortcut equation, or our short one for the shortcut. But the trick is you have to remember to double it, because you will forget to do that. And I'll have to write times 2 on your paper. The time, right? This is only the time it takes to go up. We want to know the whole time.
I see. This is another way to get the equation that we just did, right? No,
We're finding time.
Oh.
That was the displacement. That was peak height.
Okay.
Okay, so I got about t equals 1.53. And that's the time only to go up. So if it takes 1.53 on the way up, that means it's got to take 1.53 on the way down. So times 2, 3.06 seconds. At an object's highest point, or its peak height, what's its velocity? 0. And it's important to remember that its vertical velocity is 0. Okay, vertical velocity is 0. And what's the acceleration at its highest point? Does acceleration stop? Does gravity stop? No. We still have gravity acting at its highest point. So negative 9.8. Okay. Sorry, these are just a couple little things. You don't have to necessarily write these down. These are just things for you to kind of keep in mind. Okay. Peak height final velocity is important, though. Peak height velocity at 0, that's a big one. Okay, so try this part on your own. What time does the ball pass 8 meters above their hand? So he throws it upward at 15. We're going to figure out at what time does it take to reach 8 meters? This one we might have to use the quadratic on. Okay, so we'll do this one together. I won't make you do this one on your own by yourself. Okay. So here's the reason, right? We might have to use the quadratic. Do we know how fast it's moving at that point? No, we don't know how fast. We don't have final velocity. So we can't use any equation that has final velocity in it, which leaves us with using which equation? The second. Okay. So let's see here. Our second equation looks like this. Y equals y initial plus VOT plus 1/2 AT squared. Okay? We know that its final position is 8. We know its initial position is 0. We don't know time, but we know our initial velocity is 15. We know our acceleration is negative 9.8. And again, we don't know time. So here's our problem. We have a t and a t squared in our equation. Can we simplify that without using the quadratic equation?
Can we use t cubed?
Where is there a t cubed?
You can make it.
We don't multiply those two terms together. We add them together. So we can't get a t cubed out of that.
Take a t down
Nope. There's not a
leave it
t on the
down
other
if it's
side of the equation.
Nope.
You have to
Nope.
turn it into a polynomial.
Yep. Turn it into a trinomial, right? And then we use the quadratic formula. That's how it works, okay? So when we set up the quadratic formula, we want this whole side to be equal to what? 0. So we need to move 8 to the other side. And I'm going to go ahead and rearrange them in the correct order. Okay? So this term right here would be our a term because it's with t squared. Okay, so I'm going to just rearrange them here. 0 equals negative 4.9 t squared plus 15t minus 8. Right, when we use this quadratic formula, our a term's always going to be negative 4.9, right? Because it's always 1/2 times gravity. Okay, so whenever we're doing vertical problems, that's going to be our a term. So now, do we know the quadratic formula?
Yes.
Negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, 120 meters during that time. We traveled constant velocity 40 meters per second for 3 seconds. Okay, so does that make sense to you? That one's really easy for us to see. 40 meters per second for 3 seconds. We weren't accelerating here. We weren't speeding up or slowing down, right? We were at constant velocity because there was no slope. So that should be easy for us to calculate. Okay, what's happening in the following graph? Let's talk about, are we speeding up? Are we slowing down? Let's talk through the motion here. So from 0 to 1/2 a second, what are we doing? Speeding up. Good. What are we doing here? Staying the same. Okay, what are we doing here to here? Slowing down, right? Because here's our origin. Here's 0. Okay, I'll make that line a little bit clearer. There's 0. So what are we doing from here to here? Speeding up in the negative direction. Good. Now what are we doing?
Slowing down.
Slowing down. Which direction are we going?
The positive.
Negative. Still negative because we're below the x-axis. That's tricky. Tricky. Okay, so because we're still below the x-axis, we're still moving in the negative direction. But we're slowing down. That's tricky. And then here, what are we doing now? Speeding up, positive direction. Okay? So it's okay. I know it's tricky. What's the displacement of the object from 1 to 3 seconds? 1 to 3 seconds.
Oh.
It's really important you stop at the x-axis because we're only moving in the positive direction. We only want positive displacement. Okay? So, let's find the area here. We can't find the area of this, boys. We can't find the area of this crazy shape, right? So we split it into shapes that we do know. Okay, we split it into a square and a triangle. So 1 times 3, which is 3. 1 times 3 divided by 2, which is 1.5. Right, did I do that right? Okay, so we traveled 4.5 meters during that time. And it was in the positive direction because it was above the x-axis. Okay, positive direction. What's the displacement from 3 to 5?
3.
1 times 3, 1.5, and 1.5. So 3 meters in the negative direction, right? We were still going in the negative direction. Here we were speeding up. Here we were slowing down, but still moving in the negative direction. Okay? Okay, that's it.